Hello friends, I Pankaj Dumka welcomes you all to this session of fluid mechanics. So in this particular lecture, I will be talking with you about how to find out the hydrostatic pressure forces on a surface which is curved. And in the previous lecture, I explained you the method or the procedure to find out the resultant hydrostatic pressure force on a plane surface. Now, the thing which makes a curved surface different from a plane surface is that when you look the plane surface, and as you know that hydrostatic pressure force will always be uh, perpendicular to this particular surface. So all the forces, hydrostatic forces at different points, they all will be parallel. So to add them up like a scalar, it becomes very easy. Just simple integration can do the task. But if you have a curved surface, then at each and every point, let us say at this point, the pressure will be normal. The pressure force will be normal. And this point also, it will be normal. Likewise, at every point, this will be normally acting. Okay, so in this particular case, it becomes very difficult to add all the forces because they are acting in different directions. So what is the strategy? The strategy is to resolve all the forces in its components and add the components like let us say this is x direction, so add all the component in x direction, then add all the components in y direction, and then to find out the resultant, that will be the this is let us say horizontal, this is let us say vertical, so horizontal square plus vertical square. So this is the strategy which is normally followed to find out or evaluate the resultant hydrostatic pressure force in any curved surface. Okay, so to understand that how to do this, let us consider a curved surface. Let us say that this is the one, okay, and let us make this general curved surface. So let us say that this is some general curved surface which is submerged in water or any fluid, I'm sorry, in any fluid. Let us say this is the one. Okay, assume this axis to be x-axis and this axis following right hand rule. So x, y, and this will be z. So assume this axis, and what this axis is telling us, let us say that this axis is resting on the free surface of water. Okay, so assume that this is the free surface of water where the axis is resting. Okay, now what we can do is to find out the hydrostatic pressure force acting on this particular surface. What we have to do, we have to resolve the forces in all the possible directions. Okay, so the what we do is we assume a elemental area on this particular surface. Let us say this elemental area is dA. The total area is A. One more thing which I want to tell you is that assume that the water or the fluid is on the left side, this side of the surface. Okay, so what is happening here? The pressure force at this particular point will be depending on what? Let us say that this is the free surface. Okay, this is sort of free surface, and this will be depending on what? This will be depending on the depression of the element from the free surface. So the result, let us say that this depression is sorry, this is z. Okay, so this height is z, let us say. Then the pressure force which is acting at this particular point on this particular small element will be in downward direction like this, and normal at this particular point. So let us say that the unit normal vector in this direction is eta. So the pressure force which is acting at this particular element will be what? This will be rho GH, that is the pressure at this point, times the area of this element. Okay, so this is now clear to you. Now, what was the strategy? Strategy was to resolve this into all the possible directions. So let us assume that this unit normal vector is making an angle alpha with the x-axis, beta with the y-axis, and gamma with the z-axis. Okay, so this unit normal vector in the vector in the direction of which this small force is acting. So the component of this particular force in the x direction will be what? Rho g h dA cos alpha. Likewise, this will be rho g h dA cos beta, and this will be rho g h dA cos of gamma. So this is the x component of force. This is the y component of, oh, sorry, this is y. This is the y component of force, and this is the z component of this force. Okay, I hope this thing is clear to you. Now, if you look very closely, what is this dA cos alpha? dA cos alpha is the direction cosine of this small area. What is this? This is basically the projection of area on a plane which is normal to x-axis, that is onto the plane which is basically ZY plane. So if you do this, if you project this onto this particular plane, then you will be getting some area. Let us say this is the area which you got, and let us name this area as DAX, that is projected area on the x plane, that is the plane which is perpendicular to x-axis. So therefore this dfx now can be written as rho g h dAx. Okay, what is h in this particular case? H is nothing but this z. Okay, so if you are comfortable with h, then that's good. If you're not, then replace this by simply writing it as z. Okay, now what is dfy? Dfy will be rho gh. Now I'll be writing z, and this is dAy, that is projection of this onto a plane which is perpendicular to y-axis, that is zx plane. Okay, likewise, what is dfz? That is rho g z dAz. What is this? This will be the plane on the free surface of water. So let us say this is that particular area, that is dAz. Okay, projection. And dA y will be into the paper, that means on xz plane. Now if you integrate these, then you will be getting the forces, that is rho g z dAx fy will be rho g z dAy, and this again integrated, and fz will be rho g z dAz. Now the question is on what area we should be integrating. So as you can see here, this is the small element of the projection of this particular small area. This area, this is the projection. So this has to be integration over the projected area onto the x plane. So let us say that the projected area onto the x plane, the projected area onto the x plane is this. Let us say this is the projected area onto the x plane. Okay, this is AX. Then what is this? This will be rho g, this is AX, and this becomes z dAx. Likewise, this also be equal to rho g integration over z, which is the projection of this area onto this x z plane. Okay, so this is a z z d a y, and this is rho g onto the plane. Okay, so what is that plane? Let us say this, sort of something like this, let us say. So this is, let us say, the projected plane AZ. Okay, so this is in AZ, ZDAZ. Now, if you look clearly, this is what? This is the first moment of area with respect to what? With respect to this axis. Therefore, this is rho G centroid. Okay, Z centroid times area projected X. Likewise, this will be rho G Z centroid AY. Leave aside this point for the time being. So, the hydrostatic pressure force in any horizontal direction will be what? Rho G A H center of gravity. What is this H center of gravity? This is the centroid of this particular area from here. So, that is H center of gravity or Z center of gravity, ZC. Okay, so in this way you can find out the horizontal, so you can find out the uh, resultant, sorry, you can find out the component of the resultant hydrostatic pressure force in any horizontal direction. So what is this? This is the pressure force acting on any vertical plane. This is the component of that which is acting on any vertical plane which is normal to that particular axis. So to make this thing clear, let me take a simple problem. So consider this as the free surface of water and you have a curve like this. Okay, let us assume that I am interested in knowing that what is the horizontal component of force acting on this particular curve. So what I'll do is I will project this onto a vertical plane. Okay, let us say this value is x and this is some y. Okay, now so this becomes my area now. So this becomes my projected area now. So the centroid of this will be y by 2. So this ZC in this case becomes x plus y by 2. So what is the component of force which is acting on this in the horizontal direction? So Fx, let us say this is the x-axis. So this Fx will be equal to, oh, so let me call it x prime, some distance. So this will be rho g projected area. So let us say the projected area. Let us say that this is a curve like this, which is moving into the paper. Okay, curve in this direction it is flat. Let us say moving by a distance L. So this is y into L, a rectangle. If you will view from here, it will be a rectangle of y unit this and L unit into the paper. So the area of this will be, let me write it this here. So the area will be rho g, Ly will be area and z center of gravity, that is x prime plus y by 2. So in this way you can find out the horizontal component of this hydrostatic pressure force on any curved surface. Now what about the vertical component of this hydrostatic pressure force? Now if you look the Fz, it is rho g z daz. What is this? If you closely examine the situation, what is happening here, you are getting a volume. This is the volume now. Okay, so what is this daz? This z daz is nothing but the volume of the fluid from the curved surface up to the free surface. Okay, so this is the for the element. So if I write Fz, which was rho g az zaz, this will be nothing but volume. dV, and this is nothing but rho GV. So what is this V? This is the volume of fluid above the curved surface up to the free surface of fluid. Okay, so what is, whenever you have a curved surface and you are interested in knowing that what is the uh, vertical component of resultant hydrostatic force, so you do what? You take the surface, let us say this is the curved one, you take this from the surface, you project it upwards like this up to you arrive at the free surface. Then the volume of fluid above the surface up to the free surface and the weight of that particular volume will give you the resultant um, the component of hydrostatic pressure force in that particular direction. So to make this thing clear, once again consider the same problem which we have taken, that this is the curve, okay, and you are interested in what is the force acting on this curved surface. So look, if this is the case, then you do what? You move from the surface up to the free surface. So you arrive here. Okay. So this was symmetric. So what you will be able to see, if you look it from this side, you will be able to see this. Mm, you will be able to see this volume. Okay, so this is the volume whose weight is nothing but this F Z, sorry. Okay, so in this case this is symmetric in this direction, and assume that this is a rectangle, sorry, this is a quarter circle of radius y. So this is y, this is also y, and this is x prime. So what is the volume? Volume will be area of this quarter circle, that is 1/4 pi y square plus area of this rectangle. So this is y, this is x prime, so this is x prime y into length which is moving into the paper. So that's why the vertical component of force, that is Fz, becomes simply rho g times this volume, that is L pi by 4 y square plus x times y. So this is what the vertical component of force will be. Now, this is not all. There will be situation where you will not be finding a free surface above the curved surface. Then how to proceed in that particular cases? So in those particular cases, what has to be done is you have to draw an imaginary curved surface. So let me explain that problem also. So consider that uh, this is a curved surface, okay, and you have fluid on this side, on right side of this curved surface. Consider this situation. So this is the curved surface and you have fluid like this, and you are interested in knowing but that what is the hydrostatic pressure force which is acting on this curved surface in vertical direction, Fy. As you all know that that has to be in the vertical direction up, but you don't have any free surface above this curved surface. So what we do in these cases, we imaginarily extend the free surface line and then we move up, project this, then this becomes our volume into the paper. If it is symmetrical into the paper, then this becomes the area, and when multiplied by that particular length will becomes the volume. So this what has to be done when you don't have a free surface above that particular curved surface. Now this can be one of the cases. There is one more special case which is normally asked in most of the competitive examinations, and that is, let us say that instead of free surface, you don't have the free surface. Now you have a cylinder, you have a box like this. This is the curve on which you are interested to know that what is the hydrostatic pressure force in the horizontal or vertical direction. But you don't have any free surface, then how to proceed? Okay, then what is given that at this point you have pressure P. Okay, if this fluid is of density rho, and at this point if the pressure is P, then if you remove the lid, let us say that I have removed the lid, then if same pressure P has to prevail, then this rho has to be there up to some height. So what is that imaginary height? Okay, so what is that imaginary height? That will be equivalent to this pressure. So this P can be written as rho g H equivalent. So that H equivalent will be P by rho g. So you do what? You move from this surface up to a height of H equivalent, which is P by rho g, which was the pressure originally at this point in the closed envelope, and then you make a free surface like this. So this becomes now your imaginary free surface. So this is imaginary free surface. Okay, and now you can very well find out the volume. So this becomes the area, and when multiplied by the length into the paper will give you the volume, and you can find out that what is the force. So this is the force in the z direction, but not, this is not the direction, because fluid is not on the left side of this curve, fluid is on the right side. That's why I have written prime. So the direction, the actual direction of the pressure force, though the magnitude will be given by this only, but the direction, the actual direction will be this. So the actual z direction will be this. And once you know this, once you know fx, fy, fz, so the resultant force will be given by fx square plus fy square plus fz square. One thing more, that whenever you have a curved surface, let us say this is the fluid, you have calculated the horizontal direction force fx, the vertical direction force, let us say fz. Only two dimension you are showing. In the z direction, in the y direction you are not interested. Then the resultant force will always be such that if you draw a tangent at that particular point where the force is acting, that has to be normal. Why? Because if it is not normal, then there must be some component which is tangential, and that will cause the motion. And you know, because why that is causing motion? Because you know fluid cannot resist tangential forces. So if in any static field you are experiencing a tangential force, that simply means that is not a static field. Okay, so remember, whenever you have a curve, then the resultant force should always be passing through a point, and in such a way that it is normal to the tangent at that particular point. Then only the situation remains a static case. Okay, so in this particular lecture you have understood how to find out the component or the resultant hydrostatic pressure force in case of a curved surface which is submerged in a fluid. Okay, in this lecture till this point only. So if you liked my video, then please do like, share and subscribe. Thank you very much. Take care.